Welcome back. So the last time we set out to prove the inverse function theorem in more than one variable calculus. We first motivated why we cared about it. It's to solve nonlinear systems of equations. So the strategy of the proof, so what does the inverse function theorem state anyway? If f is CR, where R is at least 1, we started off with R equals 1. So if f is C1 and the derivative at a point A, the matrix is invertible, then f is locally invertible and the inverse is also C1. That's what we want to prove. So the first step is to find a small enough ball around that point where the function is actually 1 to 1 when restricted to the ball. In fact, on that ball, we proved that it's more than merely 1 to 1. We proved an inequality that implied that f was 1 to 1. And on that ball, the derivative of f was invertible as well. Okay, we chose that ball cleverly enough so that all these things happened. The next order of business is to show that f is, the image of f contains a neighborhood of the point f of a, which is what we'll do now. Okay, so what do we want to do? We want to prove that every point near f of a is in the image. That is, more precisely, the image of f contains an open ball of radius, say r dash. Then u equals f inverse of r dash intersect this, which is an open set in Rn, will be such that f from u to this, right, is 1 to 1 and onto. So, right, okay. So f inverse of this ball intersect this this smaller ball will be an open set where f is, I mean this mini, where this is 1 to 1, it's obviously onto, but also this will be an open set. This is what we want to say. Okay. So in fact, what we will prove is that the image of f contains an open ball, image of f on BA of R, so that we don't even need to take this. Okay. So that this is merely BFA of R is open. By the way, why would this be an open set? You can define U to be this, sure, but why would it be an open set? This is open because f is continuous. Once again, I am appealing to this exercise that I want you to do to show that a multivariable function being continuous is exactly the same as saying the pre-image of an open set is open. A multivariable function from an open set in Rn to an open set in Rm, not an open set, to Rm, the codomain, is continuous if and only if the pre-image of an open set in Rm is an open set in Rn. Okay, this is an exercise which I told you to do, which is crucial. Okay. So the pre-image of an open ball will always be an open set. So if we choose our open ball to be if we choose it intelligently enough, then the image of this open set is the open ball. I mean, this is contained within the original ball where f is already 1 to 1. So it is 1 to 1 and onto an open set, which means f inverse exists. In fact, the proof will then show that f inverse is actually also continuous, and then we'll prove that f inverse is C1 and so on and so forth. Okay? So this is, if you wish, the most delicate part of the proof. Okay? That is, what we want to do is, we want to produce an R dash to be so small such that for every b in this, there exists an x in here, so that f of x equals b. That's what we mean, right, by this statement. The image of f contains an open ball, which means what? Everything in this open ball is there in the image of f, which means for every b in this open ball, there is some x in this ball, so that f of x equals b. Okay? In fact, there exists a unique x. If there exists one, then it will be unique by our first part of the proof. Okay? Right. So in other words, you basically have to solve a nonlinear system of equations. This is the problem, right? How do you solve a nonlinear system of equations? So there are a number of ways to do this. One way which we will not pursue, but this is the most common way in most textbooks, including, for example, Rudin, is to solve this by using Newton's method. If you're familiar with numerical methods, how do you find roots of a function? Suppose g of x is this. Well, how do you find a root of this function? G of 0 is 0. What you do is you solve, the way you do this is the derivative at xn times g of xn. Basically, you approximate g of x by its linear approximation and solve that linear function being equal to f of x minus being equal to 0, right? So that's one. You set up this Newton's method and you prove that as n goes to infinity, these xn's actually converge to something. That's one way to do it. It's a complicated way and you have to keep track. There's a lot of bookkeeping involved. Okay. A more elegant method, and if you want a reference, you can look up this book by Mankers on multivariable calculus. That more elegant method is as follows, right? So given C in this ball of radius r dash, which we have to figure out, we want to find some x, but let's call this x dash, so that f of x dash is C. So the idea is to consider this function g of x as equals norm of f of x minus c square over an appropriate compact set Q and you minimize it. This is the idea. Minimize it. In other words, how would you figure out what this, if there was a solution to it, how would you have characterized it? One way is to take norm of f of x minus c whole square. If there is an x dash so that f of x dash is c, then of course g of x dash equals 0, and that's the minimum possible value of g because g is always greater than or equal to 0, right? So we turn this strategy around to find said x dash by minimizing this function over an appropriately cleverly chosen compact subset of BA of R, so that, and proving that the minimum of G is actually 0. If we manage to do this, then we would have managed to successfully find an x dash so that f of x dash is C. Okay, this is the crucial idea, right? So what appropriate compact set must we choose, right? That will also dictate how large R dash ought to be, okay? Right, so how does one do this? Okay, so firstly, Q is a closed rectangle, or if you prefer, or a closed ball, whichever you prefer, okay, lying entirely in BA of R, right, around A. Okay, obviously you can choose any closed there are lots of infinitely many closed balls around A lying completely within BA of R. DF is invertible when X is in Q, and you can also, for good measure, impose this. But this is not rocket science, right? Because of course BA of R was chosen so that the derivative was invertible on the closure of this ball, and it satisfied this, right? So on any closed rectangle around A lying completely within BA of R, this is true, okay? Right, okay. So Q is compact, and hence G achieves its minimum, a minimum, right? Now there are two possibilities. The minimum lies on the boundary of Q. The other possibility is the minimum lies in the interior of Q. Why don't we choose Q to be a closed ball? Maybe that's the simplest thing, because we've been choosing balls so far instead of rectangles, yeah? Okay, so in other words, Q is, let's say, a ball of radius some epsilon, okay, closed ball. That is, this is the sphere of radius epsilon around S. This is the actual ball of radius epsilon. So these are the two possibilities. Okay, 1 and 2. Let's analyze both possibilities. Let's start off with 2. That is, if the minimum is achieved in the interior, that means the minimum of G is a local minimum because it's achieved on an open set. Therefore, the gradient of G at this point is 0. Remember, if you have a local minimum on an interior point, the gradient is 0. Why? This follows from, for example, one variable calculus, right? You take any small enough line passing through x dash, then the one variable derivative is 0, and by the chain rule or any other way if you want, the gradient dot the velocity vector of that line is 0. So the gradient along that direction is 0, and this is true for all directions, so the gradient is 0. Okay. Now what is the gradient of G? What is G after all? G is this, which is the dot product of f of x minus c with itself. So the gradient of G is the gradient of f times f of x minus c plus f of x minus c times the gradient of f which is twice the gradient of f times f of x dash minus c, gradient of f at x dash. This is 0, right? Now the point is the gradient, this is not quite the gradient of f. Technically speaking, it's yeah, okay. So the gradient, it's not really a good idea to call this the gradient of f. It's more like the derivative of f, right? Maybe a better notation so that we don't confuse ourselves is the gradient of f is the derivative of f at x dash times f of x dash minus c. Yeah. So this is 0 implies f of x dash equals c. Why? Because the derivative of f at x dash is invertible. This is an invertible matrix. Okay? By hypothesis. Okay? So the second possibility is actually a very good one, because that directly implies that at this minimum f of x dash is equal to c. So we need to rule this out. So we need to rule out the first possibility. Notice so far we have not placed any restriction on how small r dash ought to be. We will do so now. Okay? So the aim here is now to rule out the first possibility. Ruling out 1 by imposing r dash to be sufficiently small. Okay, this is the strategy. Okay. So choose an r dash so small such that this ball does not intersect f of the boundary of Q. Okay, so this needs a picture, right? This is A, this is R, actually this is Q, right? What's the boundary of Q? Let me, this red part is the boundary of Q. Yeah. Now, let's see. Let's, for example, so you have F, right? Now, F takes the boundary of Q to some set, right? Now, a priori, so the question is, why is f of a not intersecting this set? Okay, the point here is on this ball, f is 1 to 1, right? Which means since a is already going to f of a, no point on the boundary of Q goes to f of a, because a is already going to f of a and f is 1 to 1, which means the distance of f of a to f of the boundary of Q is strictly positive. Notice, okay, here is one more little thing that I assume here. F of a compact set is compact. Maybe A continuous function takes a compact set to a compact set. So this follows, you can try to prove this by using the definition depending on how you define compactness. So for example, what is a compact set for us? Compact set is one where every sequence has a convergent subsequence. So if you have a sequence xn, and if it has a convergent subsequence, f of xn must have a convergent subsequence. Why? Because xn has a convergent subsequence, right? F of that convergent subsequence is some subsequence of f of xn. Why does that converge? Because what does it mean for a sequence to converge? Let's say the convergent subsequence of xn, let's call it ym, okay? Then ym converges to y. So f of ym will converge to f of y. Why would it converge to f of y? Because of continuity. So in other words, f of xn has a convergent subsequence, namely that subsequence is f of ym and it converges to f of y. Okay. So f of a compact set is a compact set. So the boundary of Q is a compact set. So f of it is also compact. Now the distance from f of a to, so you have a function, maybe if you wish, say a function h from f of the boundary of Q, which is a compact set, to R, given by h of y equals the distance, which is norm of y minus f of a. This function is continuous, right? Maybe make it square if you prefer. This is continuous. A continuous function on a compact set assumes a minimum. That minimum cannot be 0 because f of a is not lying on this. So in other words, the distance of f of a to the boundary is strictly positive, which means if you choose a small enough ball, in fact you can choose a small enough closed ball around f of a of some radius, this ball will not intersect this red region. Okay, that's all I'm saying here. Okay, we are crucially using the fact that f of f is 1 to 1 here. Now this implies that we can rule the first possibility out, namely the minimum of G cannot occur on the boundary of Q. What is G again? G is the distance, G is f of x minus c square. C is in the ball of radius r dash around f of a, right? Now the point is, if the minimum of this function is achieved on this red region, then there is a problem. Why? Because then you're saying that, so in particular, the minimum is certainly less than f of a minus c square, right? And how large is f of a minus c? It is at most r dash square, right? But the trouble is, we have just agreed that if you take the boundary of Q, its distance from a is at least 2r dash. Its distance from f of a is at least 2r dash. Since C lies in the smaller ball, its distance from C is at least so the distance from f of a is at least 2r dash. The distance from C is at least r dash, right? So this is a contradiction. So this is larger than r dash square, but it is less than r dash square, and that's a contradiction. This is a contradiction. Okay. So in other words, we have chosen r dash so small that this does not intersect this red region. For such a small value of r dash, as long as C is that close to f of a, if you perturb f of a only by this much amount, then there is always some x so that f of x equals c. That's the point. Okay, so we have ruled out the first possibility, and the second possibility says that we have indeed we have proven this. Okay. So far we have found a small enough neighborhood around A so that f is 1-to-1 on that neighborhood, and the image of this neighborhood is an open ball around f of A. Okay. Now, in fact, we can prove now that f inverse is continuous on this ball. There are a number of ways to do this. Yeah. Notice that on this, so the point is f from u to this ball is your desired map. F inverse takes it here. Note that on u, we already know, for example, that f of x naught minus f of x1 is larger than this, right? So if I take f inverse of y1, y naught minus f inverse of y1, we want this to be less than epsilon if these two are close, right? Now the point here is this is x naught and this is x1. This is f of x naught and this is f of x1. This is larger than 1 divided by this, which means x naught minus x1 is less than alpha times delta, right? So you can make this less than, you can choose delta to be less than epsilon divided by alpha, right? And therefore ensure that indeed this happens whenever this happens. This is one way to prove that f inverse is continuous. There are other ways to prove it as well, but this is one way. Okay? Right. Okay, so far what we have managed to do, once again, is we have taken the point A, f of A. We have managed to successfully come up with some neighborhood u that takes this to a ball of radius r dash. Okay? Okay, this is f of u. And f inverse exists, this is 1-to-1 on 2 here. F inverse exists and it is continuous. This is what we have managed to do, right? The next step is to show that f inverse is C1. Yeah? How does one show that? Well, firstly, f is differentiable with the expected derivative. Derivative of f inverse equals df at the point f inverse of b, the inverse of this matrix. Okay? So how does one show this? So the point is, if I take f inverse of b plus h minus f inverse of b, let's call this k, okay, I would want to show that this is equal to this times h plus an error term, which when divided by h goes to 0 as h goes to 0. That's what differentiability would mean, right? Now the point is, this means f inverse of b plus k equals f inverse of b plus h, and because f is 1-to-1, we can apply f on both sides and not lose anything, any information, and get this. Okay? Right, so how does this help? So we would next need to use the mean value theorem and so on and so forth to see how this will help. So the next time we will continue, and we will finish the proof of the inverse function theorem, and then we will move on to other things related to it, namely the implicit function theorem and so on and so forth. Okay. So thank you for joining me. So we'll stop here.